This is the first and only video for chapter 17. In this video, we're going to be looking at the synthesis of esters and amides. So if you recall these two functional groups, esters implies that there's carbons on either side of this middle portion, the ester. Amides, likewise, the implication is there's carbons on both sides, and this is an amide functional group. There's very famous compounds with both of these groups. For example, aspirin contains an ester, and penicillin contains an amide. Actually, it contains another amide here. This is penicillin. There's actually several different analogs of penicillin depending on what this R group is. So they're like penicillin A, B, C, so on. And this is aspirin. So clearly these functional groups play an important role in natural products and organic chemistry. The synthesis of esters can be seen here generalized, and so like most of our reactions, you can understand the net reaction focusing on the carboxylic acid end and how it joins with an alcohol to produce an ester. And then the other thing to notice is the groups attached to both functional groups on both sides just tag along for the ride. So those groups are variable, opening up routes to synthesizing virtually any kind of ester using this kind of chemistry. The detailed mechanism involves several steps. All of them are known to us, in fact, from the chemistry we've done before, except there is one new step, and I'll show you when we get there. So the alcohol acts as a nucleophile, forming a bond to the carbonyl carbon. And so this is similar to the chemistry we've seen in chapter 15. More than similar, basically identical. Nucleophile, nucleophilic attack, forming that bond. And the bond that was just formed by that is this bond. Notice the electrons have been swept up onto the more electronegative oxygen here. A deprotonation step, and here I just used water for the deprotonation, but that's nothing new to us. Just remove that proton and we get to here. This is the one new step in that this OH group is essentially a leaving group. It's not a great leaving group, but under certain conditions, it's an okay leaving group. Electrons can come down from this oxygen to form a carbonyl group and internally displace OH as a leaving group. So we have internal displacement of the leaving group. And those arrows result in this carbonyl group reforming, basically. It's the same carbonyl group that started out with. And then the new bond to the oxygen, which came from the alcohol nucleophile. But notice that the product is an ester. So you can know the net reaction and you can know the mechanism in detail for more breadth. Amides can be synthesized in precisely the same way. So focusing on the functional groups involved, the carboxylic acid and the amide, the amine, it's going to form an amide. And we see the amide functional group formed in the middle from those two functional groups. So you can know the net mechanism and know that these other groups are along for the ride just like before. And so we have access to a limitless variety of amides. Basically the same mechanism. the amine nitrogen acts as a nucleophile. And we define nucleophiles as Lewis bases, essentially, electron pair donors that form bonds and that form bonds. Excuse me. So the result of that arrow is this new bond. Updating our formal charges, we end up with a nitrogen that's plus and an oxygen that should be minus. And similar deprotonation step using water, although you could probably use another molecule of this amine to deprotonate, in fact. But either way, simple deprotonation leads us to this point. We have the same internal displacement of the leaving group OH. And finally, our amide bond, the new amide bond right there, amide functional group. So clearly, if you go back and review the previous one, you'll see that these are virtually identical, with the exception that you're starting with an alcohol above or an amine below. And those give rise to esters and amides, respectively. Look through some examples of this. Again, we can know the net reaction and know that basically this OH group is going to join with this carbonyl group to form an ester, and the OH is going to be kicked off as a leaving group. The electron arrow pushing mechanism, as we saw before, begins this way. It goes through those additional steps, deprotonation, internal displacement, and leads to the ester. The amide here, again, I keep saying that, amine, excuse me, nucleophilic attack on the carbonyl, like that, forms that new bond after the same steps, and we get our amide. So you could practice these two reactions, writing out all the full mechanism like we did above. Here's another one where we start with the same substrate, carboxylic acid. Notice we start with carboxylic acids for all these. And then on the top we have it reacting with an alcohol. On the bottom we have it reacting with an amine. So the left portion of the molecule stays the same because it comes from this. The right portion varies into an ester or an amide. And again, you can go through those same steps. I'll just show this arrow for the top one. Beginning like that, you get an O minus. You deprotonate. The O minus comes back in and kicks off the OH, and you end up with the ester here. Same thing happens with the amide. And again, you can go through the detailed mechanism of that on your own for practice. Finally, we can't let this go by without pointing out some of the most important organic compounds that exist, which are amino acids. So an amino acid has a carboxylic acid end and an amino end. See that? Oop, this is all the carboxylic acid end. What you can do is join two amino acids together via the amino end of one and the carboxylic acid end of another. So we need two amino acids, and these two amino acids can join together, and when they do that, they form what's called a peptide. Peptides, as can get larger, you can keep adding amino acids, and eventually they form proteins. So this is a nice segue at the end of organic here. For those of you going into biochemistry, because biochemistry largely is the study of proteins. So here we have two amino acids. This one's called valine, and this one's called tryptophan. And the structures are a little daunting, but if you go back up here again with the amino acid, what you see here is that the R group on the central carbon here, which is chiral, by the way, can vary. So then you have the amino group and the carboxylic acid group. So that's the general structure of an amino acid, where the R group can vary. And in biochemistry, you'll see the 20 essential amino acids, I think they're called, and they're all the same except that the R group varies. So the two amino acids we're looking at here, valine and tryptophan, just differ in the R groups. Notice that. And these groups will just be spectators again. What we have this set up to do is the amino group reacting with the carboxylic acid group, just like we saw above with an amine and a carboxylic acid. So the initial reaction there is the formation of this bond, and now I've just stripped away to the central portion here. So what we're looking at here is this portion, right? That's this whole thing, essentially. Our deprotonation step, deprotonating up here, gets us to this. Our internal displacement step, formation of the carbonyl group, of the amide, what will be the amide, kicking off the leaving group internally, gets us to here. And then if we just fill in the rest of it, we have this final molecule here, a peptide formed from two amino acids. The new amide bond is right there in the middle. And we stuck our R groups on here, and the names of peptides are as simple as you can get. They're just the names of the two amino acids. So valine tryptophan is the name of this peptide. And if you added another amino acid like leucine, it would be valine tryptophan leucine. And they have these abbreviations, val, trip, like that. And like I said, so once these can continue to add on both ends, so the carboxylic acid end can react with an amino end of another amino acid. The amino end can react with the carboxylic acid end of another amino acid. And so the chain can extend in both directions. And eventually becomes a protein. First a small protein, then a large protein. So very important chemistry, formation of esters and amides. And just a brief mention, the formation of the esters is the subject of the last lab of Chem 112 lab that some of you have already done perhaps. So, all right, that's the end of our only video for chapter 17. The rest will be practice problems.